Many times in chemistry, we represent molecules in a variety of different ways. For example, let's look at C4H10. This simple form is called the molecular formula. It tells us the most basic information about the molecule. However, it tells us nothing about the structure. Let's think about drawing a Lewis structure for this molecule. Lewis structures gives us a simple two-dimensional structure that shows the bonding of the molecule, as well as the lone pairs of the molecule. Let's try just a simple 4-carbon chain here, and if there are only single bonds, we would need 3, and then 2, and then 2, and then 3 hydrogens, or 10 total hydrogens. So in this C4H10 Lewis structure, we can see that we really have butane. Are there any other possibilities for C4H10? We can think about this final CH3 group, or methyl group here. It doesn't have to be added to the end of this chain. Instead, it could have a 3-carbon chain where this methyl group comes off the central carbon instead of the terminal carbon. This would still be C4H10, but it's no longer butane. The longest carbon chain is 3 carbons long, so propane, and there's a methyl group on the central carbon. So this would be 2-methylpropane. So you can see that the molecular formula of C4H10 actually gives 2 fundamentally different molecules. You can see that because they have 2 different bonding and different names. When we have the situation where you have the same molecular formula, but different molecules, either because of how their bonds are made or what their shape is, we call these isomers. So in isomer, you have the same molecular formula, but different bonding, a different shape, or orientation. In this example, butane and 2-methylpropane are actually structural isomers. So these are structural isomers, same atoms, but different bonding. One way to show the difference with these structural isomers is to write the structural formula of these 2 molecules. So butane is just a simple carbon chain, so CH3, CH2, CH2, and CH3. To indicate the difference with 3-methylpropane, we have the following structural formula. This is a different way that chemists can indicate the different structural isomers without drawing the Lewis structure or the line structures. The line structures would look like this. Another way that chemists can represent molecules is to try to indicate their 3-dimensional structure on 2-dimensional paper. For example, methane has a structure that's really in 3 dimensions, and it spreads the 4 hydrogens as far away from one another as possible. This structure is called tetrahedral since it's really like 4 points of a pyramid around a central carbon. When you look at this structure, you can see that 2 of these hydrogens are in the same plane as the paper that you're looking at. One hydrogen is coming towards you, or out of the page, and one hydrogen is going away from you, or into the page. The way that we represent this is to draw the bonds with the 2 hydrogens that are in the plane of the paper the same way we usually do. The next step is to draw the hydrogen that is going away from you with a dashed line. This indicates that it's fading away or going away from you. The hydrogen that is coming towards you appears a little bit larger than the other hydrogens because it's closer to your eye. Therefore, we indicate this by using a dark wedge. It's a bit larger to show that it's closer to you. This representation is called a dash and wedge representation. This is used as the next step to try to indicate the three-dimensional structure of molecules. Let's look at a simple example here. We have one central carbon that has 4 different things bonded to it: a methyl group, an OH or hydroxide group, a hydrogen, and a chlorine. This dash and wedge representation shows us that the methyl group and the hydroxide group are in the same plane of the page. The hydrogen is coming towards us, and the chlorine is going into the plane of the paper or away from us. If we think about rotating this molecule slightly, so let's rotate the molecule a bit so the hydroxide and the methyl group are now pointing away from us. We would see that both of the hydrogen and chlorine atoms are now coming towards us. This is still a dash and wedge representation, but it's a little bit cumbersome. This is sometimes represented using what's called a Fischer projection. Fischer was the first to use these representations to explain complex carbohydrates that have a number of carbon atoms that have many different substituents. In this Fischer projection, the lines of intersection is where the central carbon is. The vertical lines are used for the bonds that are going away from us, which is the methyl and the hydroxide in this example. The horizontal lines are used to indicate the bonds that are coming towards us. So we would have the hydrogen on the left and the chlorine on the right. Fischer projections are commonly used because they're simple ways to draw molecules and translate their structures to the dash and wedge representation. Here's a more complicated Fischer projection example. Here we actually have 2 different carbon atoms that have a number of different substituents on them. You can see the first carbon on the top has an amino group, and the second carbon has a hydroxide group, and both carbons also have hydrogens and chlorines. Dash and wedge representations can also be used to indicate this very particular isomer that is shown here. First, you can think about translating the vertical bonds into bonds moving away from yourself, and the horizontal lines as wedges that are coming towards you. From this, you can see that the amino group on the first carbon is going to be in the same side of the molecule as the hydrogen on the second carbon. If you want to think about rotating this molecule to represent this in a true dash and wedge orientation, you can see that the bonds moving away from you are really all in the same plane of the molecule. Now the amino group is on the same side of the molecule as the hydrogen on the other carbon. This makes chlorine and hydrogen on the same side of the molecule as well. I hope this video was able to show you examples of how chemists use a variety of representations to illustrate molecules. Thanks for watching.